everyone. Next we shall move on to the topic called minimum description length principle. Minimum description length principle is a powerful inductive inference and it can be used in statistical modeling, pattern recognition and machine learning. Here as you can see, minimum description length principle depends on the hypothesis. So hypothesis that we have defined with the maximum posterior probability. So already we have discussed maximum posterior probability in the earlier sessions. So based on this maximum posterior probability, so means what? Here out of the set of hypotheses, it will find or it will provide us a most probable hypothesis. So most probable hypothesis which is defined or which is denoted in terms of small h, and this minimum description length principle can be defined with the help of maximum posterior probability. So as you can see here it is motivated by interpreting the definition of Hmap in the light of basic concept from information theory. So here the statistics, the basic concept of statistics and information theory is needed to understand the concept of minimum description length. And this equation we have already discussed. Hypothesis of maximum posterior probability is equal to or max of. So as I have already indicated, it finds the most probable hypothesis based on what? So based on the maximum value out of all the hypotheses. So here or max of this is probability of D given to H into so probability of H. So as we have already seen in the earlier sessions, here probability of H is nothing but probability of this hypothesis and probability of D given to H is nothing but probability of the data so which is given to hypothesis. And this capital H indicates a set of hypotheses that we define, but small h indicates the most probable hypothesis, and which can be equivalently expressed in terms of maximizing the log function. So here we are going to see the log function, so where we can maximize the function, that is Hmap. The same equation can be expressed in the form of log function, which is log of. So here we have in terms of x into y, and when we try to expand this or when we apply this log of x into y, then we can have log of x plus log of y. So log of probability of D given to H base 2 plus log of probability of H given base 2. Okay. So and in the next step you can see, or alternatively minimizing the negative of this quantity. In this equation you can find the positive quantity which is that is plus log function of probability of D given to H and plus log of probability of H base 2. So in other way, alternatively we can have the negative quantity of the same function by replacing this maximum value as minimum value. So same equation can be rewritten in another form, alternatively minimizing the negative of this quantity as Hmap is equal to org max. So left hand side you can find the same hypothesis, most probable hypothesis, but the same equation can be expressed by considering the negative quantity of log function, which is minus log of probability of D given to H base 2. Similarly minus log function of probability of H base 2. But instead of having the maximum value, here we are going to have the minimum value. So same, the most probable hypothesis can be defined in this form, that let us call this as equation 1, and this equation 1 can be interpreted as a statement that short hypothesis are preferred. So what is our understanding between these two? So here by considering the minimum value of the negative quantity of this log function or the probability of this function, we can have the short hypothesis, assuming a particular representation scheme for encoding hypothesis and data. So let us see further how we can make use of this equation. Further, this Hmap. So Hmap is the hypothesis, that is most probable hypothesis based on maximum posterior probability, and this equation can be rewritten in this form, that is org minimum H belong to H, and here so LCH of H Okay. So in the earlier equation, so it was probability log function of probability of H. So that can be rewritten as, so L of that is LCH of H. So LCH of H is nothing but, or I can say, so L is nothing but the description length. So here this L indicates the description length of H, that is small h. So most probable hypothesis, and under optical encoding for set of hypothesis capital H. Okay. And similarly, so we have another L, again this is also description length L, but here which is considered for the data given to H. So there is a difference between these two description length. The first description length is for hypothesis H, and next description length, that is for the data given to H. And this we have the CH and CD given to H. So we have CH and CD given to H, and as you can see here, CH is the optimal code for hypothesis space H. Okay. So CH is considered as the code. Okay. So code is the optimal code for hypothesis space H, and similarly the CD given to H is nothing but describing, and of course this is also the optimal code. Okay. Optimal code where it describes or describing data D, assuming that both the sender and receiver know the hypothesis. So based on the minimum description length, okay, or we can call it as, so instead of calling minimum, first let us understand the description length, so which helps in optical coding, optimal coding, which helps in optimal coding. And if we consider the minimum of the description length of H as well as the description length of D given to H, then finally we can have the minimum description length. And of course the here the minimum description length, that is the code, optimal code D given to H, which will be known to both sender as well as receiver. And in the next step we can have the minimum description length, and in a short form we call it as MDL. Principle recommends choosing the hypothesis that minimizes the sum of these two description lengths of equation. So of course here finally we are going to have the minimum of these two. So minimum of the summation of these two. So this Hmap. So here the left hand side you can have always, so at left side always we will have most probable hypothesis, but in the previous case, so we have seen most probable hypothesis can be defined as the maximum value of the probability of H as well as the probability of D given to H. But here in this case, so we are going to have the most probable hypothesis based on the minimum description length. So same equation can be written, and this equation we call it as minimum description length. And minimum description length principle. So this is the principle. So finally we are going to have this equation, which is, so HMDL. So instead of considering MAP, so we can also consider this as that is hypothesis, which indicates a minimum description length which is equal to org minimum LC1. Instead of calling as CH and then CD given to H, straight away we can have LC1, because this gives one optimal code and the other one C2 gives another optimal code. Or minimum of minimum description length, that is L of C1, and then so minimum description length of C2, that is D given to H. So finally we can have this equation to define minimum description length principle, where code C1 and C2 to represent the hypothesis and the data given the hypothesis. So the one indicates the hypothesis and the other one represents or provides us the data given the hypothesis. The above analysis shows that if we choose C1 to be the optimal encoding of hypothesis CH, and if we choose C2 to be the optimal encoding CDH, then so HMDL will be equal to Hmap. Okay, so here if we consider C1 with respect to CH and C2 with respect to, so C given to, that is if we consider C2 with respect to this CD given to H, finally we can equate this hypothesis based on minimum description length is equal to hypothesis based on maximum a posterior probability. So, these are all about minimum description length principle. Next we have Gibbs algorithm. Already I have discussed some of the practical difficulties in that is Bayesian learning concept. So, one of the difficulty here is Bayes optimal classifier can be quite costly to apply. So, already I have discussed two practical difficulties. So, one practical difficulty is prior knowledge is required, but another difficulty is so it can be quite costly to apply. Okay. So, to avoid this, the expense is due to the fact that it computes the posterior probability for every hypothesis in H. As I have already discussed initially, so we can find a set of hypotheses. For all set of hypotheses, a posterior probability will be calculated, and then out of all the hypotheses, that is set of hypotheses, it will choose only one hypothesis. We call it as most probable hypothesis. So, since it calculates or computes the posterior probability for every hypothesis H, it is bit costlier. Then computes the prediction of each hypothesis to classify each new instance. So, and how, like, to overcome this problem, Gibbs algorithm was introduced. And an alternative less optimal method is the Gibbs algorithm, defined as follows. So, here choose a hypothesis H from H at random according to the posterior probability distribution over H. So, what we used to have in the earlier cases, so we used to have a maximum a posterior probability based on the maximum value out of or a set of hypotheses, but in this case, instead of finding out each and every or instead of finding out the maximum hypothesis or the most probable hypothesis out of or set of hypothesis H, in this case choose a hypothesis H from H at random. So, randomly one hypothesis will be chosen out of many hypotheses according to the posterior probability distribution over H. Use H to predict the classification of the next instance X, and so once it chooses the hypothesis randomly, then we can have this hypothesis, that is small h, to predict the new instance. So these two are the steps that we follow in Gibbs algorithm, but again there are some disadvantages of Gibbs algorithm. So given a new instance to classify, the Gibbs algorithm simply applies a hypothesis drawn at random according to the current posterior probability distribution. So as I have already indicated, it randomly chooses one hypothesis to predict the new instance. Okay. And surprisingly, it can be shown that under certain conditions, the expected misclassification error for the Gibbs algorithm is at most twice the expected error of the Bayesian optimal classifier. So Bayesian optimal classifier always works based on most probable hypothesis, which is again based on maximum posterior probability. But here when we just look into the error, misclassification error in the Gibbs algorithm, which is always almost like is at most twice the expected error of the Bayesian optimal classifier. The reason is here it chooses the hypothesis randomly. Instead of having the maximum value out of or set of hypothesis, here it will have the hypothesis randomly. So that is one major disadvantage of Gibbs algorithm. Next we shall see naive Bayes classifier, which is the most popular classifier in Bayesian learning concept, and of course which is the most popular classifier out of other classifiers especially. So we can have this classifier, naive Bayes classifier, so when we have large amount of data. And as you can see, the Bayesian approach to classifying the new instance is to assign the most probable target value. So as we have already seen, that is Vmap given the attribute values A1, A2. So here it works based on the attribute values, and it works based on the training examples, and of course in the training examples attributes are very, very important, and these attributes can be defined as A1, A2, so AM that describe the instance. And you can see the equation, already we have seen this equation in Bayes theorem, that is maximum posterior probability which is equal to arg max of So here probability of this Vj, so given to A1, A2. So this will be calculated, a posterior probability. So remember, this is a posterior probability. A posterior probability can be calculated based on the attributes A1, A2, so till An, and use Bayes theorem to rewrite the expression. So we have already seen Bayes theorem, and we are going to replace this posterior probability as, so probability of course it is a conditional probability. So we are going to have a conditional probability as probability of A1, A2, so given to Vj, and this is nothing but a prior probability, and here in the denominator you can find a probability of A1, A2, An. So we consider this as a evidence which is always independent of hypothesis. Okay. The first part is always the likelihood function, likelihood probability, and the second part is a prior probability, and in the denominator you can find the probability based on these attributes which is always independent of the hypothesis, and sometimes of course since it is independent, since the denominator 1 which is independent of hypothesis, so we can ignore this function. And here, so you can see here we are trying to ignore this function. So argmax of probability of A1, A2, An, this Vj, and of course this is a prior probability, and later this function can be written as, okay. So this function can be written as a product of probability of Ai and then Vj. Of course I varies from, so like I is a different value, so which varies from 1 to n. So we can replace this function as a product function, product of probability of Ai and Vj. Okay, so it depends on the number of instances, number of training examples, right. So this I value varies based on the training examples. Yes. So now if you just look at naive Bayes classifier, here naive Bayes classifier argmax of, so now we have just replaced this as the product of probability of Ai given to Vj. So as I said, I depends on the training examples, and this probability of Vj is nothing but a prior probability. So we are not going to have the denominator probability because which is always independent of hypothesis. So finally we can have this function. So based on this function, so we are going to classify the new instance. Let us see example or illustrative example based on this equation, where VNB denotes the target value output by the naive Bayes classifier, an illustrative example. So now we shall see the illustrative example based on this naive Bayes classifier equation. Okay. So in this example you can see, let us apply the naive Bayes classifier to a concept learning problem, that is classifying days according to whether someone will play tennis or not, right. The below table provides a set of 14 training examples of the target concept play tennis, where each day is described by the attributes outlook, temperature, humidity and wind. So let me read this. The below table provides a set of 14 training examples. Okay, so we are going to see the table here, and here we have 14 training examples of the target concept play tennis, where each day is described by attributes. So how many attributes we have? We have 4 attributes. Outlook is one attribute, and the second attribute is temperature, third attribute is humidity, and the fourth attribute is wind. So based on these 4 attributes, now let us see how we can classify the new instance or the new example, or we can also call it as test sample. Now if you just look at the table, so we have got 14 examples here, so D1 to D14, and so we have taken 4 attributes like outlook, temperature, humidity, wind, and finally the outcome. The outcome is yes or no, that is play tennis, whether we can play tennis or not based on these attributes. So you can also observe here, so in some instances or for some training examples you have no, and for some training examples we have yes. Now based on the prior knowledge, okay, based on the prior data or the prior probability, or I can say prior knowledge, we can find out or we can classify the new instance whether it is going to be yes or no. Okay. Now let us see this. use the naive Bayes classifier and the training data from this table to classify the following novel instance. Novel instance is new instance. So, we have new instance. Now, let us see how we can classify this instance or the sample based on, see here when you just look at this, outlook is equal to sunny, outlook is equal to sunny, temperature is equal to cool. Okay. See, under this temperature we have hot, mild, cool, okay, but out of all three, so the new instance has come as temperature which is equal to cool, humidity is equal to high, okay, and wind is equal to strong. So, our task is to predict the target value. So, which is the target value? This is the target value, isn't it? So, target value, so yes, I mean target value is yes or no. This is a new instance, this is a new instance, right, and target value is yes or no of the target concept play tennis for this new instance. So, this is our task. So, we need to classify or we need to predict the new example or the new sample whether it is going to be yes or no. So, when we look at this equation, so we have just now defined this equation. So, naive Bayes classifier can be considered as org max of, this is a prior probability, and the product of probability AI given to Vj. So, as I said, this I depends on the training examples, and in this case you can observe. So, probability of, let us have the target value as yes or no, and a prior probability V, that is probability of this Vj. So, how we can let us see how we can find out a prior probability. So, out of 14 training examples, you can see here, out of 14 training examples, so we need to find out how many target values have yes and how many target values have no. Okay. Considering this table, so let us check how many training examples says yes and how many training examples says no. Okay, let us count here. So, let me consider only as 1, 2, 3, 4, 5, 6, 7, 8, 9. So, that means we have 9 out of 14. So, we have 9 out of 14 says yes. Okay. And how many training examples says no? 1, 2, 3, 4 and then 5. So, we have 5 out of 14 says no. So, based on this we are going to have a prior probability. Let us see that. As we have calculated, probability of play tennis is equal to yes. How many? Which is 9 out of 14. Okay, says yes, and similarly 5 out of 14 says no. So, we need to find out the probability. So, for the first one, that is for probability of yes, we get 0.64 and probability of this no, which gives 0.36, right. So, this is nothing but a prior probability, Now, so we have defined as a prior probability. Now, what is our job? The next job is to find out the probability of outlook is equal to sunny, temperature is equal to cool, humidity is equal to high and wind is equal to strong. Because this is the given task or this is the new instance. You can find out in the previous slide. You can find out the same here. Outlook is equal to sunny, temperature is equal to cool, humidity is equal to high, wind is equal to strong. So, based on these attributes, so we are going to classify this new instance. Okay. So, and of course based on the prior knowledge. So, now we are going to classify this new instance and based on this data and of course based on the prior knowledge. And here if we consider similarly estimate the conditional probability. See, we have defined or we have calculated a prior probability, but we need to find out a conditional probability. Conditional probabilities, for example, so here only 2 values are taken here just for an example. Those for wind is equal to strong. Okay, wind is equal to strong. Probability of wind is equal to strong given to play tennis yes, right. So, how we can calculate this? Please keep this Please remember here probability of this strong, that means wind is the parameter or the attribute under this. So we are considering only strong, and so how many training examples which has strong, finally it gives out yes. Finally it gives out yes. Okay. So and similarly out of these samples, training examples, okay, how many has strong, right? How many has strong, and finally it gives out or, so we get no. So that we need to calculate. So let us go back to the table and check. When you look at this table, so let us see how many training examples which has strong, which says yes, and how many training examples which has strong and it says no. Let us count only S. So here let us consider only strong. So here so we have strong here which says yes, that is 1, and we have strong which says yes 2, and of course we have another, that is at D12 we have strong which says yes. So how many are there? There are 3. So there are 3 out of 9 training examples, because here out of 14 training examples, so 9 training examples says yes. Okay, but out of again 9 only strong. So wherever you find this strong which says yes, so that is this is 1, then 2, 3. So that means 3 out of 9 says yes. Similarly, so if you consider the strong, same parameter but which says no, so you can just count. So we have 1, then we have 2, next, so here the last one D14, so we have one more. So we have totally we have 3. So 3 out of 5, because out of 14 9 says yes and 5 says no. But here since we are considering only strong, in that strong, so 3 out of 9 and 3 out of 9 says yes and 3 out of 5 says no. So with this, so we can calculate conditional probability of strong given to yes. So 3 out of 9 which is 0.33, and probability of this strong given to no, which is 3 out of 5. So we can calculate this, and we have calculated only this part, the probability of, because we are multiplying all the conditional probabilities. So here we have calculated only for the probability of wind. Okay, so probability of this wind, especially strong, given to the target function. Okay, yes or no. So we have calculated this, and similarly, so we need to find out the rest of the conditional probabilities based on the same, so with respect to the same equation. Here we have calculated only for the probability strong given to this Vj, that is target function. So it could be yes or it could be no. So we have calculated this value. For the first one you get 3 by 9, and for the second one you get 3 by 5. Similarly, if you consider the first conditional probability, that is probability of sunny given to yes or no, you can see here. So we have probability of sunny given to S is equal to 2 by 9. If you follow the same concept, from the table, then you would be getting probability of sunny given to S is equal to 2 by 9, probability of sunny given to no is equal to 3 by 5, and if we consider the second conditional probability, which is probability of temperature, which is cool. So probability of cool given to S is equal to 3 by 9, probability of cool given to no is equal to 1 by 5, and the third probability is probability of humidity. Okay, humidity, that is high, given to yes or no. Okay, so you can see here probability of high given to yes is equal to 3 by 9, probability of high given to no is equal to 4 by 5. And once we calculate these values, right, so what we need to do here, we are going to multiply these values. So for separately for yes and then no. Okay, as you can see here, so here we are considering only yes. Okay, so we are considering a prior probability of yes, and similarly probability of that is conditional probabilities, conditional probability of Sunny, okay, Sunny given to S. So, Sunny given to S. So, here we need to substitute all these values. So, here we are considering only S values, probability of Sunny given to S, that is 2 by 9, and probability of Cool given to S, which is 3 by 9, okay, which is 3 by 9, and here, so probability of High given to S, which is 3 by 9, and Strong given to S. So, as we have already calculated in the earlier slide. So, all these values should be substituted. So, finally, like here you can see here, so we are multiplying all these values, okay, it is a product of these conditional probabilities. Finally, we would be getting 0.0053, and then similarly we have to find out the probabilities for no. So, again prior probability as we have calculated, and probability, conditional probability. So, probability of Sunny given to no, which is 3 by 5, and probability of Cool given to no, then which is 1 by 5, probability of High given to no, so 4 by 5, and Strong given to no. So, again we have calculated in the previous slide. So, finally we get 0.0206, okay. So, we have obtained two values here. Out of these two values, okay, after calculating these two values, now, so we need to classify the new instance based on these values. Again we have calculated a posterior probability for both yes as well as for no, okay. We have calculated a posterior probability for both yes as well as for no. Now, thus the null Bayes classifier assigns the target value play 10s is equal to no. So, why it is assigning, why it is predicting the new instance as no? Because out of these two values it should find out the maximum value, okay, or it should come up with the maximum value. And if we compare these two, so of course this is the maximum value. So, since this is the maximum value, finally the target value will be no. So, no to this new instance based on the probability estimates learned from the training data. So, we had 14 training examples. Based on the training examples and based on the conditional probability, okay. So, we have calculated a posterior probability both for S and for no, and out of these two a posterior probability we have to find out the maximum a posterior probability. So, here since this one has a maximum a posterior probability, okay. So, now the new instance can be assigned, can be considered, or the target value should be no, right. So, by normalizing the above quantities to sum to 1, calculate the conditional probability that the target value is no given the observed attribute values. So, same value can be substituted, but in the denominator, so we are going to add these two values, but here this does not make much difference both in the posterior probability, because it is common both in yes and then no, okay. So, since it is independent of hypothesis, sometimes we try to ignore this, but for normalization, so we can have this function. Finally, we get this as 0.795. So, based on this data, so we can assign the new instance or the target value for the new instance as no. So, this is one illustrative example based on Bayes classifier. Thank you.